All right, so we're back to the TS diagram, which is a little more operationally significant. And you'll notice at the very first paragraph on the left, it says, this type of diagram, this TS diagram, is most frequently used to analyze energy transfer in system cycles. And it's because we don't use the fusion line. We don't get low enough energies to start talking about anything that occurs, sublimation or fusion. We're generally talking about vaporization and condensation. So it's important to note, once again, there are two KNAs here. Can you explain the terms on the TS diagram? One of these terms is the critical point, and then define the critical point. Well, let's do that. We're going to divide this in half, this TS diagram, and we're going to put a point right here. I will tell you that that is the critical point. Don't confuse the critical point with the triple point. Remember, the triple point occurred at really low temperatures and pressures, and it was where all three phases were distinguishable, and it was about 32.02 degrees and 0.089 psia. So it's creating a vacuum in your freezer, and you can see all three phases. It's kind of like when you look inside the ice cube and you see a little blob of water in the middle of the ice cube. It's surrounded by the solid, and if the solid was given off a vapor, all three of them would be existing at the same time. Well, here, this is the critical point. We don't show the triple point, and what we're going to do is we're going to define that critical point, but first we're going to look at a couple of things. We're just going to start looking at pressure lines. Here's a very low pressure line. Let's say that this is 1 pound absolute. And then I'm going to go up and say this pressure line is atmospheric pressure. And then this line is 100 pounds, absolute. 500 pounds, absolute. 1,000 pounds, absolute. You can see that when they reach this line right here, at each of the individual pressures, this being 1 psia, and I'm going to just put psia so everyone knows the unit for all the lines, and we said this was atmospheric. I think this was 100, 500, and 1,000. At each time, regardless of the pressure, when they reached this blue line just to the left of the critical point, we know that that's when they became a saturated liquid on this line. So this line here is referred to as the saturated liquid line. And also it's true on this side of the critical point, we know that once they've reached all the way over to this line, they've become a saturated vapor. So the blue line left of this critical point is known as the saturated liquid line. And over here on the right-hand side, this is referred to as the saturated vapor line. That's this versus this. They are separated by the critical point. Above the critical point, we can see that there is no latent heat of vaporization, and all the phases are indistinguishable, and we're at a fluid up here. Indistinguishable, the exact opposite of the triple point. I can't distinguish anything of phase above the critical point. So the critical point is the point below which, if you're reading along, right-hand side, it represents the highest temperature and pressures at which a gas and vapor can exist as, very key, distinguishable phases. So everything below the critical point, I have distinguishable phases. When I get to the critical point, very important, latent heat of vaporization equals 0. There's no line, there's just a point. This occurs at a very high temperature and pressure. If you're looking, 705 degrees and 3,208 pounds absolute. The latent heat of vaporization at the critical point is 0. Steam and water are essentially the same. So critical point separates the saturated liquid line for all of the pressures and it from the saturated vapor line. Anything above the critical point, the phases are indistinguishable.